Good morning, dear friends. Myself, Dr. C.S. Ahir. So, yesterday we started this third chapter, ionic equilibria. So, in this ionic equilibria, we study this different type of concept. So, last lecture we complete this. What is electrolyte, non-electrolyte? These electrolytes are classified in three types: strong, weak, and moderate electrolytes. Degree of ionization. So this dissociation, extent of dissociation, we called it as a degree of ionization. So how this degree of ionization is defined? So it is a fraction of total number of molecule of electrolyte that split or ionize into cation and anion is called as a degree of ionization or degree of dissociation. It is represented by symbol alpha. So degree of dissociation or ionization alpha is calculated by formula number of molecule ionized or dissociated upon or divided by total number of molecule. So this degree of ionization generally increase with dilution and maximum at infinite dilution. Again we complete these factors affecting on degree of ionization. Nature of electrolyte. Weak electrolyte shows less degree of ionization, strong electrolyte shows high degree of ionization. Nature of solvent. Polar solvent shows high degree of ionization than the non-polar solvent. Concentration of electrolyte. If you have very dilute solution, this degree of ionization is higher than concentrated solution. Temperature, increase of temperature, increase the dissociation constant or degree of ionization. Presence of common ion. So this effect reduce or decrease the degree of ionization due to common ion effect. Again we start this ionization constant of weak acid. So it is a general HA is a weak acid dissociated in water solvent to form hydronium ion and A minus. So we apply this law of mass action and we have this Ka, that is the ionization constant of weak acid, is equal to concentration of H plus into concentration of anion divided by concentration of undissociated acid, and it depends upon temperature. This Ka value depends upon temperature. So we take this example. So we complete this example. This ionization constant of weak acid Ka is also related to degree of ionization alpha and concentration C. So we take this example: dissociation of acetic acid into acetate ion H plus. C is initial concentration. These ions are zero at initial stage. At equilibrium stage, this alpha amount of acid undergo dissociation, that is degree of dissociation is alpha. So remaining part is, so C alpha is acetate ion, C alpha is H plus ion. So this alpha amount is reduced from C. So C minus C alpha. We can take C common, the bracket remaining 1 minus alpha. So this is the concentration of acetic acid at equilibrium, which is undissociated. So we put this value in equilibrium and we get this K. What is K? Dissociation constant of weak acid. It is the product of concentration of acetic ion, acetate ion, concentration of H plus divided by concentration of undissociated acid. So we put these values: C alpha into C alpha, C square alpha square upon C into bracket 1 minus alpha. This C is cancelled with square, so remaining C is here, alpha square. C is get cancelled, so remaining is 1 minus alpha. So what is the relation? This Ka, that is the ionization constant of weak acid, is equal to C into alpha square upon 1 minus alpha. So this is the relation of ionization constant of weak acid with concentration and degree of dissociation or ionization. So again we start this ionization constant of weak acid in yesterday's lecture. So consider an ionization of weak base BOH in an aqueous solution at equilibrium. So we consider this BOH as a weak base. It dissociated B plus and OH minus in water. So water is excess, we consider it as a constant. So in equation we don't represent that plus water, it is an excess quantity. So in final equation, applying law of mass action, Kb, here Kb is a ionization constant or dissociation constant of weak bases, B for base. So it is a product of concentration, multiplication of product of concentration of ion, that is B plus concentration OH minus concentration upon concentration of undissociated base. where the square bracket represent molar concentration in moles per liter of each species. Hence, the ionization constant of weak base Kb is a characteristic constant and equal to the product of molar concentration of cation and hydroxyl ion, that is OH minus, divided by the molar concentration of unionized base. So this is the unionized base. So Kb varies only with temperature of ionic equilibrium reaction. So this reaction is affected only by temperature change. So we consider this particular example. This ionization constant of weak base Kb is also related to degree of dissociation or ionization alpha and initial molar concentration C of weak base. So consider general ionization of weak base. Particular example is this ammonium hydroxide NH4OH is a ammonium hydroxide act as a weak base. In aqueous solution, we have this reaction, this ammonium hydroxide in water or aqueous solution dissociated into NH4 plus ammonium ion and OH minus, that is hydroxyl ion. So at initial molar concentration there is only ammonium hydroxide, so its concentration you consider as a C moles per liter. There is no ionization, so this concentration of ions are 0. When this reaction attain equilibrium, this equilibrium concentration is, this degree of ionization is alpha. So this alpha amount of ions are, this alpha is the degree of ionization of this hydroxyl ammonium hydroxide. So it produces alpha into C, that or C into alpha hydroxyl ion, same amount C into alpha ammonium ion hydroxyl ion. So this C alpha amount is decreases from C concentration. So C minus C alpha, taking C outside, remaining is 1 minus alpha. So C into bracket 1 minus alpha is a equilibrium concentration of undissociated base, that is ammonium hydroxide. Where at equilibrium unionized ammonium hydroxide concentration is C into bracket 1 minus alpha, and this equilibrium concentration of this ion ammonium and hydroxyl is C alpha, that are equal. So according to equilibrium law, we have this Kb, ionization constant of weak base, is equal to concentration of ammonium ion into concentration of hydroxyl ion divided by concentration of weak base ammonium hydroxide at equilibrium. Putting these values, same C into alpha upon C into bracket 1 minus alpha, C square alpha square, C is cancelled with square, remaining C is there, alpha square upon bracket 1 minus alpha. So this is the relation between ionization constant of weak base to concentration and degree of ionization. So mention here. So now we consider this ionization constant and ionic product of water. So ionic product of water and ionization constant. When we consider this pure water, there is no impurities, is very weak electrolyte. Its ionization or dissociation is very small extent. Till we consider this ionization of water, liquid, it at equilibrium it produces H plus and OH minus, proton and hydroxyl ion in aqueous solution. Pure water, see here water is itself act as a solvent, so there is no need of solvent. Water itself act as a solvent, and the solvent molecule undergo ionization, and at equilibrium it produce very small extent of ions. Dissociation is very small extent. So pure water has unique amphoteric property. What is amphoteric nature? So it is a dual nature. It acts as an acid as well as a base. This is water act as acid as well as base, so it is called as a amphoteric properties. In presence of acid it acts as a base, and in presence of base it acts as a acid. For example, we consider two molecules of water. Suppose this first molecule acts as acid, so property is it gives H plus ion to base. So this water is converted into conjugate base OH minus after loss of proton. So proton is lost, remaining part is OH minus. So this base, this water molecule, due to amphoteric nature act as a base, it receive proton from acid. So this water is converted into conjugate, this base water is converted into conjugate acid, hydronium ion H3O plus by receiving proton from acid, and we get this conjugate acid base pair. So according to equilibrium law, we have this equilibrium constant as K is equal to concentration of hydronium ion, concentration of OH minus upon concentration of water. See, this concentration of water is constant, very large extent. You take in singly. Pure water is very weak electrolyte. It ionizes or dissociated to a very small extent. And thus, when we consider this concentration of water, it is this concentration of undissociated water remains constant, which is very large extent, because ionization is very less. This concentration of concentration of water we consider as a constant, new constant, that is small k. And we know this hydronium ion is actually concentration of H plus ion, so we put this concentration of hydronium ion as a concentration of acid H plus. So this above equation become substituting value. Hydronium ion is a H plus concentration into OH minus upon K, this new small constant K for concentration of water. This K is shifting in direction. We have this equation. This capital K and small k is equal to new constant Kw, and this Kw we called it as a ionic product of water, and is equal with concentration of H plus ion into concentration of OH minus ion, and this is called as a ionic product of water. So it is the product of molar concentration of hydrogen and hydroxyl ions in pure water. So this equation very important. This ionic product of water Kw is equal to multiplication of concentration of H plus ion into concentration of OH minus ion. So at 25 degrees centigrade temperature in pure water, the concentration of H plus ion has been experimentally found to be 1 into 10 raised to minus 7 moles per liter. See, this water having very low ionization, so it shows H plus ion concentration at 25 degrees centigrade experimentally observed at 1 into 10 raised to minus 7 moles per liter. Therefore, we know that this H plus ion and OH minus concentrations are same, equal to with this quantity 1 into 10 raised to minus 7 moles per liter. Since ionization of water produce equal amount of hydrogen and hydroxyl ion, and thus by equation Kw, that is ionic product of water, is equal to H plus ion concentration into OH minus ion concentration. We put this value 1 into 10 raised to minus 7 moles per liter for H plus ion, same into OH minus ion 1 into 10 raised to minus 7 moles per liter. This multiplication gives Kw is equal to 1 into 10 raised to minus 14. So this multiplication is minus 7 become minus 14. So 1 into 10 raised to minus 14 moles per liter at 25 degrees centigrade temperature. That is important. So this ionic product of water is 1 into 10 raised to minus 14 moles per liter at 25 degrees centigrade temperature. Since ionic product of water is equilibrium constant, it is also equilibrium constant for ionization of water, and it varies only with temperature. Now we consider this new point, relation between ionization constant and ionic product of water. Just now we complete this ionization of weak acid, ionization of weak base. We take this particular example of both. Again we consider this ionic product of water Kw. Now we have this new point, this relation between ionization constant and ionic product of water. So this ionization constant we consider for weak acid or weak base and relate with ionic product of water. So for that we consider this simple example, an ionization of conjugate acid base pair. We take this conjugate acid base pair, this ammonium ion NH4 plus and ammonia in aqueous solution. So this conjugate acid base pair, this ammonium ion act as a acid, NH3 this ammonia act as a base, and when we add this conjugate acid base pair in water, it act as a acid base pair. See, when we consider a particular example, then this point is clear. Conjugate acid base pair, so this ammonium act as a acid ammonia act as a base, so we consider this ammonium ion and ammonia as a conjugate acid base pair. They form from each other, that is a conjugate acid base pair. When this conjugate acid base pair we consider in aqueous solution, see first ionization of acid in aqueous solution. So what is acid? NH4 plus is acid, so we take in water. What is the reaction? It acts as acid, loss H plus. This water acts as a base, receive H plus from acid to form hydronium ion, and this ammonium ion when lost H plus it converted into ammonia. So this is the first reaction for acid in aqueous solution. So applying the law at equilibrium we get this ionization constant of weak acid. So this NH4 plus is a weak acid, so this Ka is equal to concentration of hydronium ion into concentration of ammonia divided by concentration of ammonium NH4 plus. This water considered as a constant. Similarly for this ionization of base in aqueous solution, so what is base? This ammonia is base. When this base added in water, what is the reaction? Now this water act as a acid, so this water act as a amphoteric nature. In this case water act as a base. Now we can, in presence of base, water act as a acid. So what is the property of base? It accept proton from acid. Water act as acid is lost H plus, so it converted into OH minus. When this proton is accepted by ammonia, it having lone pair, proton is accepted and get converted into NH4 plus ion. So this is a reaction, equilibrium reaction. So applying this law to this above equilibrium, this ionization constant of weak base, weak base. This ammonia is a weak base, so this Kb is equal to concentration of NH4 plus into concentration of OH minus divided by concentration of ammonia. Water concentration is constant. Now you consider this multiplying Ka to Kb. K into Kb is equal to this concentration into this concentration. So in this concentration, this ammonia is in numerator, this ammonia is in denominator. This NH4 plus is denominator, this NH4 plus in numerator. So these similar concentrations are cancelled, so we represent by same color. This ammonia cancel, NH4 plus is cancel. What is the remaining part? Concentration of water concentration, protonated water, that is hydronium ion, H3O plus and OH minus. So by cancelling the common term from numerator and denominator, we get Ka into Kb is equal to H3O plus into concentration of OH minus. Again we know this concentration of hydronium ion is equal to concentration of proton. Put this concentration of proton here. So K into Kb is equal to concentration of proton into concentration of OH minus. So this concentration of H plus into concentration of OH minus, what is this? Just now we completed, it is a Kw, that is ionic product of water, and thus we get this relation. We put this relation Ka into Kb is equal to Kw. So this is the relation. This ionic product of water is equal to ionization constant of weak acid into ionization constant of weak base. Therefore this product of ionization constant of conjugate acid and base is equal to ionic product of water. In case of conjugate acid base pair, if we know Ka, then Kb. If we know this Ka value, then this Kb value, or if we know this Kb value, then this K value can be calculated from the known values of ionic product of water. If we know this ionic product of water at particular temperature, and among these two, if we know any one, then second is calculated by using this equation. So this is very important equation. So in case of conjugate acid base pair, if we know the Ka, then Kb, or vice versa, can be calculated from the known values of ionic product of water. So this much part we completed in this lecture. So remaining part we consider for next lecture. Thank you.